the second section of Chapter 8, we start exploring different shapes of polar graphs. As we graph these polar equations, you're going to see some categories of shapes emerge that we're going to discuss. We're also going to talk about symmetry. You remember from college algebra, our symmetry test was to plug in the opposite of the value we started with to see what happened. Basically, we're going to do something very similar for the symmetry test with polar equations. So let's start talking about polar grids. Now, I already introduced the shape of polar grids to you for section 8.1, so this is not a surprise that we have this concentric circle bullseye looking grid. If we plot our point 5 pi fourths, remember we find pi fourths first. Now, for the grid that you have been given, notice that they are marked in 15-degree increments. So that makes it nice. We can find our 30-degree angles and our 45s pretty simply. If I want to plot the point 5 pi fourth, I first find pi fourth, which is here, theta is pi fourth, and then I count out a positive 5. 1, 2, 3, 4, 5. Let's label this point P for simplicity's sake. And now it says to plot point -2, 5 pi 6. We're going to label this point Q. Remember, you find your angle first. So we're going to rotate around to 5 pi 6. Now 5 pi 6 is going to be over in quadrant 2. If this is my 3 pi 4, so let's see, this would be 15, 30, and another 15 and a 30. So this is going to be 5 pi 6 here. It's 30 degrees away from our x-axis. And then if this is 5 pi 6 and I go to a -2, that means I go back the other direction. So I'm going to go -1, -2, and this point is going to be 30 degrees away from the x-axis in quadrant 4. This is point Q. These points were converted to rectangular coordinates in section 8.1. Now, if you want to flip back to your notes there, that's great. Otherwise, just notice that we have 5 pi fourth became 5 square root 2 over 2, 5 square root 2 over 2. If I put that into my calculator, because if I'm going to graph this point, I need an approximation, right? If I put that into my calculator, I get about 3.5 for both of those. Now, I should have switched colors. These are my coordinates for point P, 3.5, 3.5. And then these are going to be my coordinates for point Q. -2, 5 pi 6 gave me the rectangular coordinates, square root 3 and -1. Square root 3 is about 1.7. If I think about lying a rectangular grid over my polar grid, so think about putting that square XY grid over your polar grid. Let's go ahead and regraph these points using our rectangular coordinates. Well, 3.5, 1, 2, 3.5 is right here, and then I go up 1, 2, 3.5. Right there is point P on the 1, 2, 3, 4, 5th ring. And then I go to point Q and I graph the rectangular coordinates, 1.7, -1. Well, 1.7, this is 1, this is 2. So 1.7 is going to be about here. Go down 1, sure enough, on that second concentric circle out in quadrant 4, I get point Q. We're going to go ahead and do a third point R. When we started with -3, 3, we ended up with, this is my rectangular coordinate, so -3, 3, -3, 1, 2, 3, up 1, 2, 3, right there, -3, 3. Gave me 3 square root 2, 3 pi fourth as the polar coordinate. Well, 3 pi fourth is 3 pi fourth. 3 square root 2, if I plug that into my calculator, I get approximately 4.2. If we make this point R, 3 pi fourths is in quadrant 2. This is, yep, that's 3 pi fourths, and 4.2 would be out 1, 2, 3, 4, and a little more. Yes. So we verified for 3 different points that the polar coordinate and the rectangular coordinates fall in the same location. Alright, let's talk about graphing some of these things. An equation whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy that equation, just like the graph of a polynomial equation consists of all points that satisfy that equation. Okay, we have, for example 1, we have two different graphs. So we're going to graph this first one, r equals 2 cosine theta, and then we're going to graph the second one, r equals 4. Now for r equals 2 cosine theta, let's come across to the side. R equals 2 cosine theta. That's my first one that we're going to graph. It tells us to use techniques from the last section to convert the polar equation to a rectangular equation. So we kind of know how to predict what we're going to graph. Well, my two techniques that I was given were to square both sides or to multiply both sides by r. We're going to choose to multiply both sides by r as our technique. When I do that, I get r squared equals 2r cosine theta, and then I can rewrite that, substitute in for terms of x and y. R squared is x squared plus y squared. R cosine theta is x. Now I want to graph this. I know I have an x squared, a y squared, and an x. I suspect that my graph is going to be a circle. Let's get it in correct form and see what we come up with. We've got x squared minus 2x. I know I'm going to have to complete the square to come up with the rest of that coordinate. So if I complete the square, I'm going to add in something on both sides. Take half of b and square it. Well, half of b is a -1, squared is +1. So I do a +1 to both sides. Then I find the factor of this. Well, half of b was 1, so my factor is that -1. So x minus 1 squared plus y squared equals 1. That's that graphing form of the equation of my circle right there. This gives me a center at 1, 0, because remember my equation starts out as x minus h quantity squared plus y minus k quantity squared equals r squared, where r is my radius and hk is my center. So my center is at 1, 0, my radius is the square root of 1, that's just 1. So my center is at 1, 0, right there, and my radius, I'm going to go out 1. So I need a circle with a radius of 1 centered at the point 1, 0. So there's that first equation graphed. It's the graph of a circle. Okay, let's do the second equation. Number 2 is r equals 4. This one I'm going to choose to square both sides, because when I square both sides of this equation, I get r squared equals 16. R squared, I can substitute in x squared plus y squared, and I have my equation for my circle. I haven't adjusted x and y, so my center is just at the origin, and my radius is the square root of 16, or 4. Remember, the radius is always positive. It's a distance measure. So my center is at the origin, and I have a radius that goes out 4, so it's going to hit on the axes at 4, -4. I do not draw very good circles. This is supposed to be an actual circle, not a circle-ish shape. That's the best I can do. So those are both equations for circles. When we get them into rectangular form, we can see that and graph those. Alright, let's look at this next one. We're given the equation r equals 3 sine theta. I want to put it into a rectangular equation form, so I'm going to multiply again by r, because I can see some substitutions happening if I do that. So if I multiply both sides by r, I have r squared equals 3r sine theta, and then I can do my substitutions. R squared is x squared plus y squared, and then that would be 3y, because r sine theta is y. I'm going to move that back over to the other side so that I have x squared plus, and then I know I'm going to have to complete the square. So y squared minus 3y, and then I'm going to complete the square, and then whatever I complete the square on the left, I have to add to the right. Okay, so I take half of b, that's 3 halves, and I square it. So plus 9/4 to both sides. Then I factor, I find that binomial factor, and I have, let's see, I have 3 halves, y minus 3 half, that was the half of b, equals 9/4. So that's the equation of the circle. The center at the circle is going to be at 0, 3 halves, and the radius is going to be 3 halves. So my center of my circle, 0, 3 halves is at 1.5. My radius is 3 halves, so it goes down 3 half, up 3 half, and out 3.5. So, or 1.5. So 1.5 is going to be here, and I've got my circle. Okay. Alright, so hopefully these graphs of circles are pretty comfortable and familiar to you. You can start to see how we find the equations. Let's look at a different type of graph. Now we're asked to graph theta equals pi third and r cosine theta equals -2. So first is going to be this theta equals pi third. Well, pi third, this is just an angle, right? So pi third is that angle in quadrant 1. It's 60 degrees. We're going to, it says to use the techniques from the last section. We're actually going to use a technique that is not one they showed us in the last section. For this first one, to put this equation in rectangular form, I already know that if these are 15-degree increments, I expect that I'm going to go, right through here. But just to double check, let's take the tangent of both sides. That would give me tangent theta equals tangent of pi third. Well, tangent theta is the same thing as y over x. And the tangent at pi third is square root 3. If we look at our unit circle, if we work with sine and cosine. So if I solve for y, this equation becomes y equals square root 3 times x. So let's think about some points we could plug in. If x is 0, y is 0, so yep, it's going to go through the origin. If x is 1, y is square root 3, which in your calculator, that approximation is 1.7. Pick something else. Let's pick, maybe x is 4, and we get 6.9. If we did -1, we would get -1.7. These are some points on a line, and that line goes through that 60-degree pi third angle. So there is y equals square root 3x. That's that first equation. Now let's look at the second one we were given. R cosine x equals -2. Well, r cosine x, r cosine theta, not x, r cosine theta is x. So that just is x equals -2. And x equals -2 is a vertical line. Where is x -2? Well, x is -2 right here, and every value above and below. So that is just, it's hard for me to draw a straight line against all those concentric circles. So that's just a vertical line. This is x equals -2. So these equations are both graphs of lines. Are the graphs of lines. All right, in example 4, we're given r equals sine theta, r sine theta equals -3. So, okay, let's think about this. If r cosine theta equals -2 was a vertical line, what do you think about r sine theta equals -3? Yep, that is going to be a horizontal line. Because if I look at this, r sine theta is the same thing as y equals -3, which is a horizontal line at y equals 3. 1, 2, 3. And again, have to fight against those circles to get my horizontal line drawn. Oh, -3. Shoot, guys, I'm glad I caught that. What did I do wrong? Well, I graphed the line at +3. I even got it kind of straight. I hate to undo it. See, there we go. That was supposed to be a straight line. Did not happen. Okay, so we have a horizontal line, y equals -3. So all three of those equations, when I put them in rectangular form, it's easy to see they are equations of lines. Okay, now we're going to start talking about our fun shapes for polar equations. We're going to start by talking about a symmetry test. Now I have another document that we're going to do together in our BBCU class to talk about symmetry for polar equations and look at the patterns to expect for different shapes. But we're just going to take it through our guided notes and start right where they tell us to start. So we have three different types of symmetry. You can see that you have your polar axis and then your graph goes up and down. You have your polar axis, your graph goes here, and you have a polar axis that the graph goes here. Three different types of symmetry. Which one matches to which? Well, for this one, it's symmetric about that polar axis, which is the same thing as our x-axis. So this is symmetry about the polar axis, which is the same as our x-axis symmetry. This one is symmetric about the y-axis, which is the same thing as being symmetric about theta equals pi half, because that positive pi half is the positive part of the y-axis. And then finally we have that kind of twist in the middle. That is what we are familiar with as origin symmetry. Our origin is defined as the pole when we are dealing with polar equations. Now, our test for symmetry for college algebra was to plug in a -x and to see what happened. Our test for symmetry with polars looks a little different for each different type of symmetry. We're going to start with our polar axis symmetry. Our polar axis symmetry, or x-axis symmetry, like that first example above. In the polar equation, we replace theta with -theta. So that's pretty simple. We replace theta with -theta to check for polar axis symmetry. If you get the same result, if f of theta equals f of -theta, then that graph is going to be symmetric around the polar axis. Our second type of symmetry we're going to look at is that y-axis, or pi half symmetry. In the polar equation to check for this type of symmetry, we replace theta with pi minus theta. So theta is replaced with pi minus theta to check for y-axis, or pi half symmetry. And then finally our pole symmetry, or origin symmetry. In your polar equation, you're going to replace r with -r. And we're not gonna do that second option. That's just going to be how we check. We replace r with -r. If nothing changes, if we get the same result as what we started with, then we have a graph that is symmetric with respect to the pole. Okay, now there's kind of a disclaimer here. These three tests for symmetry are sufficient conditions for symmetry, but they're not necessary. So when you do a symmetry test for your polar symmetries, if you get a positive result, you have found symmetry. But if you get a negative result, that doesn't mean you don't have symmetry. So here is what this means in words. An equation could fail the symmetry test for a certain type of symmetry, but still have that type of symmetry. So if I get a pass, I know I have that type of symmetry. If I get a fail, we're not sure. So the key here, the takeaway, is do not put too much emphasis on your symmetry tests. They are greatly helpful when you get a positive result because you don't have to check as many points. You have a good expectation of what your graph is going to look like. For example, if I know I have polar axis symmetry, I only have to check 1/2. So I would only have to check the top half from 0 to pi, and then I just reflect it down. If I know I have pi half symmetry, that y-axis symmetry, I only have to check from negative pi half to positive pi half, and then I just reflect it across that y-axis. If I have origin symmetry, I really only have to check one quadrant, and then I just reflect it across into the other quadrants. So it saves me a lot of time if I get a positive result. But just remember that a negative result is actually a maybe. We're going to go ahead and do an example of a symmetry test here so that you can see how to do the symmetry test. For example, we're going to check r equals sine of 2 theta. Now, we know that 2 theta, the sine of 2 theta is 1, right? So this graph is actually symmetric to the polar axis. We end up with, what we end up with gives us a graph that is symmetric to the polar axis. Let's check our symmetry. We check our polar axis symmetry, which is our x-axis symmetry. We do that by replacing theta with negative theta. So we do theta becomes negative theta. So I would have r equals sine of 2 times negative theta. Sine is an odd function, so r equals the negative sine of 2 theta. I didn't get the same result. I got the opposite, so it fails that symmetry test. And I just told you that it is symmetric when I graph this. It is symmetric to the polar axis. But it fails the symmetry test. So when I get a fail, I think, you know what, that's a maybe. I might have that symmetry, but I don't know. Let's go ahead and run the other 2 tests. Our x-axis, that was our x-axis. We're going to do our y-axis symmetry test. Excuse me, let me make my phone hush. My y-axis symmetry test, y-axis, which is theta equals pi half. The way I check for that type of symmetry is to plug in, where I had theta, I plug in pi minus theta. So theta is replaced with pi minus theta. In that equation, that would be r equals sine of 2 times pi minus theta, which is sine of 2 pi minus 2 theta. And that's a sign difference identity. So I need to pull out my identity sheet and say, okay, well, sign difference is going to be sine of 2 pi cosine 2 theta minus cosine 2 pi sine of 2 theta. And then I plug in everything I know. I know that the sine at 2 pi is 0, so this first product is 0, minus cosine at 2 pi is 1, sine of 2 theta. So that gives me r equals a negative sine of 2 theta. That's not what I started with. That's the opposite. So it also fails this symmetry test, so my result would be a maybe. And then my third symmetry test is to check for origin or pole symmetry. And I check for pole or origin symmetry by replacing r with negative r. So instead of r equals sine of 2 theta, I would have negative r equals sine of 2 theta, and that's not true. So that fails, which again gives me a result of a maybe, not a never. Okay, the important part of this is that I know that this equation is going to be symmetric to the polar axis, yet it fails that symmetry test. These symmetry tests are sufficient. If I get a pass, it proves symmetry. but they're not necessary. I don't have to pass to prove to have symmetry, not symmetry, goodness. Okay, we're going to graph some polar equations by plotting points. So here we go. We're going to be graphing the equation r equals 2 plus 2 cosine theta, and it's going to give us what we call a cardioid shape. Cardioid shape of our graph. Now, cardioid, cardiac, references the heart, and these cardioid shaped graphs are basically heart-shaped. Now, we get cardioid shaped graphs from two basic types of equations, the forms r equals a plus or minus a cosine theta, or r equals a plus or minus a sine theta. As long as a is greater than 0, this equation in one of these forms is going to give me a cardioid-shaped polar graph. Now, this a can be factored out. It's a common factor, so it could be factored out. A is going to be positive. Okay, we're going to start by checking for symmetry. We do our symmetry checks. Our first symmetry check is for, I've got to look back because I don't have them named on my notes. My first symmetry check is for polar axis symmetry, where I replace theta with negative theta. So polar axis symmetry, I replace theta with negative theta. When I do that here, I would have r equals 2 plus 2 cosine of negative theta. And cosine is an even function. So that gives me r equals 2 plus 2 cosine theta, which is exactly what I started with. So this is a pass. I know that my graph is symmetric to the polar axis, or the x-axis. So that is a good thing. Now I want to do the other two checks because I might have more than one type of symmetry. My second symmetry test is to check for y-axis symmetry by replacing theta with pi minus theta. So theta is replaced by pi minus theta for my y-axis symmetry. Theta equals pi half symmetry. When I do that, I have r equals 2 plus 2 cosine of theta minus, or pi minus theta, excuse me. That is a cosine difference identity. So that would give me 2 plus 2 times, and then I have sine theta cosine theta minus sine theta cosine, sine pi cosine theta. Good grief, guys, I can't speak today. Sine pi, we're doing our cosine difference identity. Sine pi cosine theta minus cosine pi sine theta. And I get 2 plus 2 times, well, sine at pi is 0. And so that makes that 0. So that is a negative, cosine pi is a negative 1. So a negative times a negative 1 is a positive sine theta, which is just, which is 2 plus 2 sine theta, 2 plus 2 sine theta. That's not what I started with. So that's a fail, which means it's a maybe. And then finally, my third check is to check for origin or pole symmetry. And I do that by replacing r with negative r. So that would be negative r equals 2 plus 2 cosine theta. If I distribute that negative to the other side, if I divide both sides by negative 1, I get negative 2 minus 2 cosine theta. That's not what I started with. So that is a fail, which is a maybe. So I got to pass over here. I got to for sure. I got to pass for polar axis symmetry. And when I set up my chart, I see that I've been told to plot the points from 0 to pi. Why am I only plotting points from 0 to pi instead of 0 to 2 pi? Well, I only have to check half because it is symmetric to the polar axis, my x-axis. So I only have to check 2 quadrants, or half the rotation. So that saved me from a lot of work because of that symmetry. What I'm going to do is I'm going to say, you know what, once I've checked every value from 0 to pi, I just reflect that across the x-axis. Okay, so let's think about what our points are going to be that we are going to graph. This is our equation. Our angle theta is 0. Where theta is 0, I would have 2 plus 2 times the cosine of 0. Well, the cosine of 0 is 1, so that is 4. So 4 is the r, and my angle theta is 0 here. At pi 6, the cosine is square root 3, so square root 3 over 2. And 2 plus square root 3 is going to be about 3.73. So this second point would be 3.73 at pi 6. What about at pi 4? Well, pi 4, I would have 2 plus, and then I've got 2 times square root 2 over 2, which is just square root 2. That's approximately 3.4. So 3.4 at pi 4th. At pi 3rd, 2 plus, well, 2 times the cosine at pi 3rd, that cosine is 1/2. 2 times 1/2 is 1, so that is 3. So that's a nice, easy one to find. And then at pi half, cosine at pi half is 0. So this is just 2 plus 0, which is 2. At 2 pi 3rd, I'm over in quadrant 2, so now my cosine function value is negative. Cosine is a negative 1/2, so that's 2 minus 1, which is 1. At 3 pi 4th, I have a negative square root 2 over 2 times 2, so that becomes 2 minus square root 2, which is about 0.6. At 5 pi 6, I've got negative square root 3 over 2 for my cosine function value, so 2 minus square root 3 is about 0.3. And my cosine function value at pi is going to be negative 1, so that becomes 2 minus 2, which is 0, so 0 pi. Okay, now our graph is kind of small. We've got to watch our angles really closely. Remind yourself that this polar graph has marked increments at 15 degrees. So everywhere you have a marked increment, you are not going to have a point. We don't have a value for 15 degrees. We have 30, we have 45, we have 60. We don't have 75. Okay? All right, so we are at, where our angle is 0, we're at 4. So 1, 2, 3, 4. At angle 0, we have 4. So at 2 pi, we're also going to have 4. That reflects there. Where our angle is pi 6, so that's up 30 degrees, we are at 3.73. So 1, 2, 3, not quite 4. And when we go down, we're going to have that same not quite 4. At pi 4th, we're at 3.4. So at pi 4th, we're at almost 3.5, and that's true down here as well. At pi 3rd, we're at 3. So here's pi 3rd, 1, 2, 3. Here's pi 3rd, 1, 2, 3. So there's another point. At pi half, we're at 2. So where my angle is pi half, we're at 2. So we're going to be at 2 where I've got negative pi half as well. At 2 pi thirds, we're at 1. 2 pi thirds is going to be 4 pi 6. So that's 3 pi 6. 4 pi 6 is 2 pi thirds, and we are at 1. So that is going to be here, right? Yep. And then at 3 pi fourths, we're at 0.6. And at 5 pi 6, we're at 0.3. and then at pi we're at 0. So we have this heart-shaped graph that reflects across the x-axis. And when I say heart shape, I don't mean like Valentine's heart. I mean like heart in your body heart-shaped graph. That's a cardioid shape. Okay, so that's our first one. We've got any function that comes in this form is going to give us a cardioid shape. Excellent. Let's look at the next one. Let's look at graphing a polar equation that looks like r equals 4 minus 2 theta. Notice that on my cardioid, these were the same values, a and a. Here we have two different values. That means that our equations that give us a limason, and that's like a French C, and without a loop, a limason without a loop, are going to be in the form of r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta, where a is bigger than b, and together the sum of a and b is greater than 0. A and b are not the sum. I'm sorry. A and b are both greater than 0. I can't even read my writing. A and b are both greater than 0. So a is larger than b, and both of them are positive values. Okay, so here we go. Limason without a loop, we want to do our symmetry test first. Our first symmetry test is for polar axis or x-axis symmetry. We replace theta with negative theta. When I replace theta with negative theta, I have r equals 4 minus 2 cosine of negative theta, and we know cosine is an even function. So that gives me r equals 4 minus 2 cosine theta, which is exactly what I started with. So this is a pass. Once again, we have x-axis symmetry, so we only have to check half, unless we have a different type of symmetry as well confirmed, in which case we don't even have to check half. So let's do our second symmetry check. We're going to check at theta equals pi half. That's my y-axis symmetry test. To do that, we replace theta with pi minus theta, so we know we're looking at a difference identity. R equals 4 minus 2 cosine of pi minus theta. There's my difference identity right there. So I would have 4 minus 2 times cosine pi cosine theta plus sine pi sine theta. And that would be 4 minus, well, cosine pi is -1, sine pi is 0. So this term goes away, and this gives me a -2 minus cosine theta. So -2 minus is a plus cosine theta, which is not the same as what I started with. So that fails, which means it's a maybe. I don't know that I have that type of symmetry, but it could happen, but I'm not going to count on it. And then my third symmetry test is that pole or origin symmetry, where I replace r with -r. So that would be -r equals 4 minus 2 cosine theta. If I multiply both sides by a negative, I would have -4 plus 2 cosine theta. That's a fail. It's not what I started with, so it's a maybe, but it's not confirmed. The only thing that's confirmed is that I have x-axis symmetry, like the last graph, so I only have to check my points from 0 to pi. Okay, once again, we are taking our angle, we're plugging it in to find that value and use it to get the polar coordinates that I'm going to graph. So this would be 4 minus 2 times, well, cosine at 0 degrees or 0 radians is 1. So that's going to be 2. So r is 2, theta is 0. That's my first point to plot. At 0, I am out here at 2. At pi 6, I have a cosine value of square root 3 over 2, so that becomes 4 minus square root 3, which is about 2.27, or we're going to just say 2.3 because the graph is tiny to start with. So at pi 6, 30 degrees, I go just past. I'm going to do that above and below because of that x-axis or polar axis symmetry. At pi 4th, I have 4 minus 2 times square root 2 over 2, which is 4 minus square root 2, which is about 2.6. So my point is 2.6 pi 4th. So I find pi 4th, and I go out a little bit more to 2.6. 1, 2.6, pi 4th, 1, 2.6, okay. At pi 3rd, about 60 degrees, I have 4 minus 2 times a half, which is just 4 minus 1, which is 3 at pi 3rd. So at pi 3rd, I'm out at 3. At pi 3rd, I'm out here at 3. At pi half, I have 4 minus, the cosine at pi half is going to be 0. So 4 is just 4 at pi half. So at pi half, I am at 1, 2, 3, 4. At negative pi half, 1, 2, 3, 4. At 2 pi thirds, my my cosine is now negative. So I have minus 2 times a negative 1/2, which is going to be a plus 1. So my point is 5 at 2 pi thirds. So at 2 pi thirds, I'm out here at 5. And down here at 2 pi thirds, I'm also at 5. At 3 pi fourths, I have 4 minus 2 times a negative square root 2 over 2, which is 4 plus square root 2, which is about 5.4. So 5.4 at 3 pi fourths and negative 3 pi fourths. So 3 pi fourths is here. It's going to be right about there and right about there. At 5 pi 6th, I have 4 minus 2 times square root 3, a negative square root 3 over 2, which becomes 4 plus square root 3, which is about 5.7. So at positive pi 6 and at negative pi 6, I'm at about 5.7, almost out there to 6. And then at pi, I've got 4 minus 2 times negative 1, which is 6. So at pi, I am at 6. And you see that I reflected it as we went. And so you've got just almost a circle. It's kind of elongated a little bit, comes in just a little bit. Okay. We have, I'm looking to see, we have 3 more shapes to go. This is already a really long video, so I'm going to pause it and we are going to pick up with a second part for our last 3 polar graphs.